A cylinder with a density ρ c, a radius r and a depth d is suspended from a cable pulley system into a liquid which has a density ρ l and a depth d. And the tank is open to the atmosphere. Now part A asks us, assuming that the density of the cylinder is greater than the density of the liquid, show that Archimedes' principle is equivalent to the difference in vertical forces due to the fluid pressure. So remember that Archimedes' principle states that the buoyant force is equal to the density of the fluid, so that would be ρ L in this case, multiplied by the submerged volume of the cylinder, so that would be pi by the radius of the cylinder squared by the depth d. So that's the submerged volume of the cylinder, and we multiply this by gravity, and that gives us the buoyant force. Now as we know, the pressure at the bottom of this cylinder is equal to the density of the liquid by gravity by the height plus the depth of the cylinder. Okay, so remember that the pressure depends on the density of the liquid and the height below the surface of the liquid. And as we know, the pressure at the top must be equal to the density of the liquid by gravity by h. And we can calculate the force at the bottom of the cylinder. So that's equal to the pressure at the bottom. So ρ L G by h plus d multiplied by the cross-sectional area of the cylinder. Okay, so that's pi by the radius squared. And similarly, the force at the top of the cylinder is effectively the density of the liquid by gravity by h. Okay, so the pressure at the top by the cross-sectional area. And therefore, the difference between these forces is equal to ρ L by g by the area. And as you can see, we're going to have h minus h is going to cancel, and we're left with d. So therefore, the difference between these vertical forces due to the fluid pressure is equal to the buoyant force, using the submerged volume here. Now part B asks us to find an expression for the tensile force in the cable. Well, what do we know about this cylinder? Well, the forces acting on this cylinder is going to be a force of weight, a tensile force in the cable, and we're also going to have a buoyant force acting at the center of buoyancy in this case. So what we have is a buoyant force as follows. So as we're told, the cylinder is suspended from the cable pulley system, so that means that the cylinder is in static equilibrium. And therefore the tensile force in the cable plus the buoyant force is equal to the force of weight. And therefore the tensile force is equal to the force of weight minus the buoyant force. So the force of weight is simply the density of the cylinder by the volume, which is pi r squared, by the depth, multiplied by gravity. Okay, so this is the mass times gravity. And then minus the buoyant force, which is the density of the liquid, by pi r squared d by g, as we calculated earlier. So therefore the tensile force is effectively pi r squared d by g by the density of the cylinder minus the density of the liquid. And as we know, according to the problem, the density of the cylinder is greater than the density of the liquid. So therefore the tensile force is positive and it's pointing upwards. And part C asks us, what is the net force acting on the horizontal surface of the cylinder? So if we draw this cylinder over here, and if we take a section of the cylinder on this side, well, the pressure due to the fluid is going to result in a resultant force acting perpendicular to that area. And at the back of this cylinder, we're going to have an equal and opposite force on that area that's opposite this one here. So we're going to have an equal and opposite force, cancelling that force out. And that's going to happen all around the cylinder. So therefore the net force is going to be 0. And I'll see you in the next video.